So today I will present the research at the Mobility Information Engineering Lab on how we use the computational movement analysis to address the issue of sustainability. The unsustainable development in the transport sector over the last century has caused many serious issues we are facing today. Excessive CO2 emissions, increasing roads taking over natural habitats, inefficient energy consumptions, noise pollution, and traffic congestion. To address those issues and ensure a livable environment for the future generation, we are at a pivotal point to make a rapid change into more sustainable ways of travel. Many new mobility concepts have been proposed in this direction. For example, shared mobility, mobility as a service, and adoption of electric vehicles. In our research at Mobility Information Engineering Lab, we utilize computational movement analysis to study and promote these new sustainable mobility concepts. Computational movement analysis refers to methods and analytical approaches to process, analyze, and visualize tracking data and movement patterns to facilitate knowledge discovery and the modeling of movement. This computational movement analysis is at the core of our research activities. We focus on developing and research innovative computational methods for the analysis, simulation, and prediction of individual mobility, with the goal of making mobility sustainable. Particularly, we have three main research avenues: sustainable mobility, computational methods, and the intersection of mobility and energy. I will demonstrate one case study from each categories in the rest of my talk. The first study I wanted to show you today on the topic of sustainable mobility is understanding the impact of mobility as a service. Mobility as a service offers users an easy access to an integrated multimodal mobility that often combines public and private transport, usually through a mobility package and a digital platform. With this easy access, mobility as a service is designed to be competitive with private car option, thus promoting users to shift from privately owned cars to this more sustainable travel. But how do people actually react on a new mobility as a service offer? And how much CO2 emissions can be reduced through the adoption of a mobility as a service offer? To answer these questions, we collaborated with SBB, the Swiss Federal Railways, and conducted a long-term tracking study to test the concept of mobility as a service. Other mobility providers that are involved in the project include BMW, Mobility Car Sharing, and Publibike, a bike sharing service provider. The tracking study has two pilot studies conducted in Switzerland. The first pilot study is called Green Class ecar study, which is launched in 2016 with 139 participants. And the second Green Class e-bike study launched in 2017 with 50 participants. In these studies, participants received a mobility as a service offer that gives them access to multiple mobility options for a fixed yearly rate. Participants in the first pilot study received a Swiss-wide public transport pass, a battery electric vehicle, a parking space at their local train station, and credits for car sharing and bike sharing services. In the second pilot study, there is an e-bike instead of e-car provided to participants. As part of the pilot study, all participants installed a tracking app on their phone and agreed to label the recorded GPS tracks with the user mode of transport and a high-level description of the trip purposes. As shown in the table, the first Green Class ecar pilot study has 227 million GPS position fixes, and the second tracking study resulted in 74 million GPS position fixes. Here are some major results from the study. This figure shows the mode split of users in the Green Class ecar pilot study. The share of ecar is represented in orange. After introducing ecar in week 4, the ecar option becomes an important component of the mobility mix. ecar mainly replaces regular car and is combined with the train and other public transport. So the data result shows that the average CO2 emissions of all users over time in the green class ecar study. You can see the blue line, which shows the moving average of 5 weeks. With the introduction of ecar in week 4, there is a clear drop of CO2 emissions. Peaks at the end of the season is mainly caused by an increasing use of cars during holidays, especially during the Christmas. For the second pilot study, SBB Green Class e-bike pilot study, the combination of e-bike and train struggles to replace individual cars. The figure shows the mode split of all users over the tracking period. The e-bike is represented in gray color and the bike option is represented in pink. The pilot study started in week 38 when users received the e-bike and the public transport pass. The combined portion of e-bike and bike grows a little bit after the introduction of mobility as a service, and then falls back to previous level quickly. The portion of the car and train are not altered significantly. Thus, we can conclude from the second pilot study, the e-bike does not seem to replace regular car portions drastically. So without the replacement of conventional car trips, the CO2 reduction from the second pilot study is not overall stable. This figure shows that the average CO2 emissions of all users in the second pilot study over the tracking period. Blue line is again the moving average with a window size of 5 weeks. Users show a reduction in their CO2 emissions in general. However, the reduction is less significant compared to the first pilot study and not so stable. In the previous study, we observed the behavior change at the aggregated level by examining the change in mode split. But how does the mobility behavior change at the individual level as a result of the mobility as a service offer? And how can we automatically detect the overall long-term mobility pattern change? Continue the exploration of the SBB Green Class data. In the second session on computational methods, I will showcase a method developed to automatically detect long-term individual travel behavior change. The method mainly utilizes a clustering-based framework. So here is the flowchart of the framework. We first extract the most important trips of individuals. This reduces randomness caused by spontaneous trips. We then calculate trip similarity based on the trip level features, including the travel mode feature, distance, and duration. And then we apply hierarchical clustering method using the similarity matrix. This gives us different classes of travel behaviors. Last, we detect the changes in the travel behavior classes over time using 2 methods, a Herfindahl-Hirschman index, HHI index method, and a sliding window method. The proposed method is tested using the SBB Green Class ecar data. The slide shows the travel behavior calculated for 1 user. In the subplot A, each colored line indicates a trip class. The proportion of the trip class shows the evolution of user travel preferences over time. The relationship between mode frequency and the trip class can be seen in subplot C. The blue color mainly indicates e-car use, and the orange color mainly indicates car use. We can see from plot A, there is a sharp increase in the trip proportion traveled in e-car at the beginning of the study period, and a decrease of car trip proportion. So this switch of car to e-car is likely a result of the introduction of mobility as a service offer. Plot B visualizes the separations of the travel behavior dimensions. in a distant duration scatter plot. The trip class colored in purple, class 16, is mostly observed in long distance and duration trips. This trip class is mainly composed of ecar and train mode. The change detection result confirms our observation as well. We can see from plot A that the sliding window-based algorithm successfully detected the change at the beginning of the study period. The HHI signals capture sudden changes in the trip class shares. We found that they mostly correspond to the peaks and valleys in the change of the most dominant trip classes. We also selected typical user patterns to validate the detected results. Comparing subplot A and B, we can see different lengths of the change period, suggesting that the user actually reacted differently to the mobility as a service offer. The pattern shown in C is a result of user that frequently changes his or her home locations. For some users, as seen in D plot, we actually did not detect travel behavior change. Also, you can see some fluctuations appeared over time. They are not so strong enough to be captured by our method. This implies we actually need to carefully define what constitutes a mobility behavior change, and then select the change threshold according to the specific application. The pre-processing of the mobility behavior change study has been implemented using the TrackIntel framework. It's an open source Python library actively developed and maintained in our lab. For more information, please check out the GitHub repository. In the last section, I want to highlight a case study on the research area of integrating mobility and energy, mobility-aware electric vehicle charging. To curb the CO2 emission, the International Energy Agency recently published a roadmap to bring global energy-related carbon dioxide emissions to net zero by 2050. The roadmap pointed out that by 2030, electric vehicles should make up 60% of new car sales globally, up from today's 5%. This rapid change of electric vehicles will, of course, pose great pressure to the electrical grid system if the charging of all these vehicles are uncontrolled and uncoordinated. Then it comes to the question, how should we satisfy the charging demand and mobility needs of users without posing severe pressure on the electrical grid? An idea is to use a rooftop photovoltaic generation to cover individual electric vehicle demand. Particularly, we wanted to know how well electric vehicle owners can cover their mobility energy demand using solar panels on their own roof. We combine the real mobility behavior of electric vehicle owners, shown by the left figure, with a solar model that is applying to their respective houses, shown in the middle figure. Then we simulate different smart charging scenarios to find out that how much of their EV-related energy consumption could have been covered if they have had a PV system on their roof. In the study, the four scenarios are evaluated. They are shown on the left through the four small plots. The base scenario, the car charges as fast as possible when it is plugged in. It is also a greedy and uncontrolled charging. In the first scenario, only minor adjustments are applied to the empirically recorded charging schedules. So here we only slightly differ the charging time. In the second scenario, any adjustments of the empirically recorded charging schedules are allowed as long as the user can fulfill their mobility needs. The last scenario, the third scenario, is similar to the second one, with an additional battery storage available at the person's houses. By comparing the four plots, we can see that if the charging is uncontrolled, as in the baseline scenario, users cannot take much advantage of their PV generation to cover the mobility demand. Well, with a good charging strategy, as shown in the second scenario, most of mobility energy demand can be covered using the rooftop PV generation. The red figure shows the greenhouse gas emission of electric vehicles for the full scenarios. In summary, smart charging in combination with the rooftop solar generation can significantly reduce the greenhouse gas impact of electric vehicles. Here are the references used in the presentation. For other related studies, welcome to check out our website. I would also like to show you our lab members. We are led by Professor Martin Robel at the Chair of Geoinformation Engineering. Thank you for your attention.
Great. Thank you very much, Yanan. And I'm looking at the questions. I don't know if there might be a couple coming on the chat or on the Q&A. In the meantime, I had one. I was curious about the tracking tool packets that you kind of briefly mentioned in passing in the presentation. And I was wondering whether you could say a little bit more about what can it do and how does it make the data scientist's life a little better when working with mobility data?
So the tracking intel framework mainly covers the pre-processing steps of mobility data. And the most unique part about the tracking intel framework is it follows the hierarchical model to extract mobility information, starting from GPS position fixes, that's the raw GPS data recorded, to state points, which is one level up as a clustering of points. And then by detecting those state points, also generate trip lags and trips and further up towards. This unique hierarchical structure of modeling mobility is also used by many transportation planners. So I think that's the, by developing this framework, we allow researchers to easily analyze mobility data and extract those different levels of mobility information.
Super. It does sound like a really useful and interesting project. We'll definitely be checking it out over the coming weeks and months. I don't know if anyone so I think I mentioned everyone who's panelists cannot ask on Q&A. So we have this back and forth that's a little tricky. Alessia, did you have a question?
Yeah, sorry, just because it's quicker than writing. Cool. Okay, so thanks, Yanan. That was very interesting. And I particularly like that you talk when you talked about electric cars, but also about energy demand. Because the main problem with switching from fossil fuel cars to electric car is that electric cars still will make the energy demand increase. So do you think that in the idea of mobility as a service, maybe this element of also providing energy, accounting for energy should be part, at least, of the policy stack, let's say?
I definitely agree. I think it has been one important component for many policies related to electric vehicle and also the agendas for slowing down the climate change. That's why the example gave from International Energy Agency, besides the projected number of electric vehicles we should have by a certain year, they also provided the guidelines for how the energy should be satisfied from different sectors of the generation. Like, I think if I remember the number correctly, by 2035, the major world economies should stop using fossil fuel generated electricity, but shift to cleaner energy source. That's why, as one pillar of our research focus, we consider how to better coupling the mobility demand and the energy demand. And also wanted to mention a new project that we recently started is to integrate the vehicle to grid strategy with car sharing. If you're interested, welcome to check out our website.
Yes, if you have a website, please drop it on the chat so everyone in the audience can see it. Any more questions or comments on Yanan's talk? I don't see anyone across the 3 different channels I'm trying to keep tabs on. So if not, I'll pass it on to Krasen for the next talk again. Thanks.